So welcome everybody. This is our very first OpenXLA community meeting for 2025. And we've got a guest speaker from Amazon. But before we kick that off, wanted just to do a recap of 2024 because what a year it was. And you'll see as we go through some of these slides about the amazing, phenomenal success that OpenXLA had throughout the year. And then once we spend a few minutes on that, I'll turn it over to Ajay, who is joining us from AWS, to talk about some of the slides that he's put together for us. All right, so the way 2024 kicked off is with an OpenXLA Dev Lab in Sunnyvale at Google. And I kind of wanted to show you this map to show how many folks traveled literally from all around the world to attend the Dev Lab in April. We had over 100 folks, 25 different industry partners. So this was definitely something that we wanted to celebrate. And if you wanted to find out a little bit more about what were some of the things that we discussed, there is a blog post. So please do go check that out. And all of the great positive feedback that we got in April, just wanted to highlight that again. So thanks to the folks who participated, who literally came from all over the world to be a part of OpenXLA Dev Lab. We appreciate it. The other thing I don't want to remind everybody of is that even Jensen Huang, not only were we mentioned during NVIDIA GTC, but he actually put on the OpenXLA t-shirt at NVIDIA headquarters in April. So wanted to kind of remind folks of that. And then we went into May 2024 with a mention at Google I/O of OpenXLA. And it was highlighted in one of the major keynotes on the stage. We also had a great Google I/O talk that was given by Shaheen, focusing on PyTorch workloads with cloud TPUs. And then I'm going to turn it over to Kevin to talk a little bit about the stable HLO release that happened in May.
Thank you. Yeah, I'll keep it brief because this is somewhat of old news at this point. But yeah, in May, we released stable HLO 1.0. This had a little bit to do with that Google I/O release. It was notably when we hit and exceeded our initial milestones for the stable HLO project, things like fully specified reference interpreters, complete a good amount of documentation and collab tutorials, dynamism and quantization also spec'd, and plenty of community-driven RFCs. But the notable feature of V1.0 was that we extended our compatibility guarantees to 5 years of backward compatibility and 2 years of forward compatibility to support on-device deployments and annual update cycles. And yeah, even plenty has happened since May. We have done some raggedness explorations. We have a new sub-channel quantized type that's been proposed to the upstream LLVM project. That's in review right now. We've added some numerical accuracy features, added plenty of support for composites end-to-end, including JAX and PyTorch APIs. And I'm planning to share more about our next year plans, but that'll happen in a future community meeting.
Perfect. Thank you so much, Kevin. And then we were also mentioned at Apple's WWDC. So wanted to make sure that we highlighted that as well. There was a blog post that Apple had put out that focused on Jackson XLA mentioned, and this got a lot of LinkedIn shares with several Spotify podcast mentions. And then in September, OpenXLA had a great showing at the PyTorch conference in San Francisco. We had a booth, and there were a lot of folks that showed up and spent a ton of time with the OpenXLA engineers. Google hosted a lunchtime reception. We also hosted an evening reception that was focused on open source, where it was attended by folks from Amazon, from NVIDIA, AMD, Intel, all of the industry partners were there. Jacques also presented OpenXLA, talked about JAX during one of his talks. We had Shaheen talking about all the great work that's been happening around PyTorch XLA. And again, the picture that you see on the right is that open source reception that we hosted after day 2 of the PyTorch conference, and it was oversubscribed. More than twice the number of people that we expected to show up actually came and stayed until the very end, until the restaurant actually had to close their doors. And then in October 2024, we got another mention at .ai. So I wanted to make sure that was highlighted as well. And then we had our DeepMind team who co-presented with CoreML at LLVM in Santa Clara. And that happened in October. And then we went into November, so it's not like Q4 slowed down at all. We had another Dev Lab that we hosted, and I wanted to kind of remind you of all the incredible metrics and the fact that this community contribution health has been really, really strong throughout 2024. So just a quick update on just kind of a mention of all the great metrics. And if you wanted to go check out, if you missed that by any chance, you can look at all of the recordings, watch that on the OpenXLA YouTube channel. And then our Penpon presented OpenXLA at Supercomputing, and she had 2 or 3 talks at Supercomputing. So OpenXLA got a huge shout out, not just in the Google Cloud booth, but also at the Intel booth and other avenues as well throughout Supercomputing over that course of the week in Atlanta. And then we rounded all out in December with OpenXLA shoutouts during AWS reInvent, which included an Amazon press release mention. And so I just kind of wanted to flash this slide up because OpenXLA was mentioned throughout the various talks that happened at reInvent. And then when I send out the email afterwards, I'll send you all the links to the Amazon press release, the blog post that we put out in December that kind of talks about JAX XLA, so everyone can take a look at that. So it's definitely been quite the year. So I can't wait for what 2025 has in store for us. If it's anything like 2024, I'm super, super excited. I think it's going to be absolutely amazing. I can't wait to see what the whole community is going to be able to do, just given the solid foundation that we've set forth in terms of what happened in 2024. And with that, I'm going to turn it over to Ajay from Amazon.
Thank you.
What I'll do, Ajay, is I'll stop sharing so that you can share your slides.
Cool. All right. Can you see my slides okay?
Yes.
Cool. Thank you. So today, I wanted to share some ideas about accelerator agnostic generative AI, and that involves OpenXLA. I'm a relative newbie to OpenXLA, so I've been working with OpenXLA only for the last 12 months or so. So in that context, I wanted to share some ideas. So we'll start with some motivation behind the ideas, look at some architectural basis for the ideas, and then talk about some optimizations that might be done in this context and some prototyping work that I've done so far and some thoughts about next steps. So the basic motivation behind the idea is accelerator agnostic training inference Python scripts. The idea being that you write some Python script for training or inference once, and then it should run inside a CUDA container or an XLA container, and then run on whatever accelerator is underneath those containers. So for example, to highlight the point, you could have that script running inside a CUDA container on GPU, or you could have the same script running on an XLA container on GPU. And the idea is that that should not be something that the person running should care about, but the person writing the script should write it in a way that this is feasible. And the thesis behind it is that this will, in some sense, increase the participation in the context of OpenXLA. People would want to use this because it would be more transparent to use it. So let's take a simple example to make this idea concrete. So imagine you wanted to do some basic GPT type of training, and you wanted to use PyTorch. So I created a concrete example of this, which is available on in the GitHub, and it would essentially look something like this. So you have a script, one script, and that script will automatically detect whatever context it's running in, and you won't have to worry about any of that. And this would be a relatively simple use case. And the reason this is a relatively simple use case is because we're not using any libraries other than native PyTorch. So this is quite feasible, and there's tons of examples running on TPUs like that with Llama and GSPMD or FSTP, and that's because these scripts rely on just using native PyTorch. But even in the context of these scripts, you will see that the examples you will find will either just run on a particular device, whatever that might be, or they run on CUDA, and they don't themselves unchanged run on any of these in any of these containers and on any of these accelerated devices. And that's sort of like the difference between the example that I'm showing you. Nevertheless, this is still a relatively simple use case. And the only time this won't work is if the underlying backend compiler of the XLA is not supporting a particular construct or a particular op that might be there in native PyTorch. A slightly harder use case example would be, say you wanted to do stable diffusion 3.x fine tuning or training and so on. And now in this case, you want to use, say, Dream Booth from the diffusers, Hugging Face diffusers library with FSTP. So in this case, because in addition to using FSTP, which is of course part of the native PyTorch, you're trying to use Hugging Face diffusers with a specific approach to doing the fine tuning, which is using Dream Booth. Now you have dependencies on these libraries. So in this context, it just so happens that Hugging Face has actually already XLA-enabled diffusers library. So even though this is a harder use case in principle or in conceptual terms, but because the diffusers library has been XLA-enabled, that helps to transform this use case into a simpler use case. And again, the only reason it won't work is if the underlying backend compiler is not providing support, but other than that, it'll work transparently. And I have tested this using CUDA containers and XLA containers on GPU. Now, the next thing is, how do we generalize this concept? So the general idea is that there is a lot of GenAI models, scripts, and training scripts, a majority, I would say, that are not accelerator agnostic. And they're basically written in the context of CUDA, and that's not surprising. And so you have tons of libraries and toolkits that only support CUDA on GPUs, and then you have tons of training and inference scripts that use these libraries. And the academic researchers, of course, overwhelmingly use these libraries, and so most of the research ends up creating artifacts that only directly run on CUDA on GPUs. So the idea is to attract academic researchers and other developers. What if we XLA-enable training and inference libraries? So that essentially means if the popular training and inference libraries that are being used out there are XLA-enabled, then people, at least in principle, can write scripts, whether they are training or inference, that could run on any device, and also would not have to trade off between some optimal pathway to an accelerator that they may consider as the best pathway versus using a different pathway. Idea being that if you want to run on GPU, maybe you want to run directly through CUDA, or maybe you want to run through XLA. Either way, it should not be something that you should have to worry about except at runtime. So what is the architecture in principle that would allow us to do that? So in order to do this, one would have to write first, very consciously, accelerator agnostic training and inference scripts. This in principle is not hard. It's just a matter of adopting a practice. But the underlying pinning for this is to be able to have XLA-enabled training and inference libraries, because otherwise you force the user to just use native frameworks, whether it's PyTorch, JAX, or so on, and that can be limiting. And that's something that the users may not adopt as regularly. And so the XLA-enabled training and inference libraries and toolkits becomes a prerequisite to make the accelerator agnostic training inference scripts possible. The rest of it is, of course, pretty straightforward, and there is nothing new or different about it. Now, in the context of optimizations, where would one do optimizations in this context? Say, by optimization, I mean optimizations for performance that are trying to leverage some accelerator features and so on. So as usual, there will be accelerator-specific optimizations in the backend of the compilers or pre-compiled kernels or different accelerators. And there are also accelerator-specific optimizations at the training inference libraries and toolkits and the frameworks. So that won't change. That would still be the case. But as much as possible, the idea would be that the libraries themselves, out of the box, would be XLA enabled, and one would not need to worry about that aspect. Okay. So to kind of put this idea to test, I did some prototyping work, and I picked the library Megatron LM, which is an open source library from NVIDIA, and I forked it, and I tried to see how far I could get by, applying these conceptual ideas and, and trying to make them work. So I've shared the GitHub link here, and I'll go to the GitHub in just a second and show you a little bit more about that. But first, how far did I get? So I was able to get far enough so that all the unit tests pass. I have not tried to run any functional tests yet. And then I have not tested on CPUs, and I've not tested on any other device other than GPU itself. But I've tested with the latest version 2.5x, or a little less than the latest version of PyTorch. And then, so 2.5x here, 2.5x here. And then the GitHub is current with the upstream. So it is actually just a few, 1 or 2 commits, either ahead or behind. So what were the challenges in this context, and what were the lessons learned in this context? So the key, the first challenge, at least in this specific context, was that this library, which is, again, a very common situation, in turn depended on many other libraries, which is often the case. And the libraries that Megatron LM depended on were libraries like Apex, Transformer Engine, and GEM, to give you some example. Now, these other libraries are very CUDA specific, so that was the first thing to tackle. As it so happens, the upstream Megatron LM was already deprecating Apex, so they were already doing a lot of work to kind of make that dependency as optional as possible, and in fact, kind of make it completely optional because they are going to deprecate it. So that was very good. And then the second aspect of Transformer Engine was also something they were trying to make it optional, which means that you could use it with or without it. So I sort of accelerated both those things, and I made sure that I could use the library by completely removing all of these 3 dependent libraries, and then still be able to use it appropriately in terms of functional and performance aspects. So that was the first piece of work. And then once you're able to do that, then of course you have to make the code device agnostic. And I would say this is relatively straightforward in terms of just removing hard-coded devices and so on. But there are some API differences in, for example, device random number generation state between XLA and the CUDA, and so you have to tackle those. But again, those are solvable, and I was able to solve them in this context. Then the other aspect that needs to be tackled is normalizing the collective communications, because again, some of the APIs are different in the way these collective communications happen between XLA and CUDA. But that was relatively straightforward on how to normalize that. The challenges that one ran into in this context were some were just bugs. It seems that some of these collective communications like send receive are not very well tested in the context of XLA. And this, I think it's because of the nature of the examples and tutorials and all, and the use of OpenXLA, and the biases that are in that context means that the coverage is not complete. And then some of the things, some distributed communication APIs like all gather object and all, they don't have any analog in XLA. So there was some stuff that needed to be done in this context. There are some open bugs that would be great if they were fixed. And then there was some fallback to using a different backend other than XLA backend for certain types of collective communications. The most tricky part in this context is, of course, directly memory map tensors, where you have a buffer, underlying buffer, and then you're mapping tensors to those through views, and then you are essentially affecting change in the contents of the memory by writing to these tensors and then using those backup of the memory mapped buffers for collective communications. Unfortunately, there's no way to do this in XLA, at least that I could figure out. And so that's something one can't use. But nevertheless, this was a relatively successful experiment, I would say, at least to the extent that I have completed it. And this gave an idea of what can one expect in this context if one wants to do this more broadly. So some further prototyping ideas, I would say doing GPT type of LLM models, Stable Diffusion 3.x type of models, these are still probably the good candidates in terms of doing further prototyping. And then doing NeMo and Megatron LM Core and diffusers, these three libraries as the starting point, it seems like a good idea, at least from my perspective. And the good news is the diffusers is already done, and it's more in terms of at least the groundwork. So it'll be more like testing, validating, and making sure that it all works on different types of accelerators. And then NeMo, of course, is the front-end toolkit to be able to use something like Megatron LM Core. And then for now, the focus has been, at least from my point of view, on PyTorch, but it would be good to extend that to JAX as well. And then what I'm proposing as an idea is to stay within the world of GPUs, at least for this prototyping effort, and then let the extension to the other accelerators happen down the road. And for benchmarking purposes, again, I'm suggesting that we stay within GPUs and sort of like benchmark CUDA on GPUs versus XLA on GPUs. So sort of like XLA container and then CUDA container. And part of the reason I'm suggesting that is that, of course, because of the broad availability of GPUs in every cloud, in every context, as opposed to the other accelerators, which are available only in specific clouds. And if we want to do a broad-based community effort, maybe that's the normalizing place where we focus our efforts in terms of doing the initial benchmarking. The other rationale for doing this would be that you're sort of like eliminating everything else, and it's just boiling down to the differences between using OpenXLA versus using CUDA. And the underlying accelerator is the same, the hardware is the same, and that is a good way to see whether what you're doing is actually, in some sense, performant across those two approaches. So the next steps, besides defining the prototyping scope and defining some sort of a community effort around it, and maybe expanding the list of suggested libraries here, the other thing would be having upstreaming discussions with library owners. So for example, the Megatron LMX work that I've done right now, That is purely a fork, and I haven't upstream anything and not submitted any pull requests and so on. So as you can see, it's pretty close to what the upstream is at this point. And just to give you a few very quick peeks of the kind of things I was talking about, I'll show you a couple of files in terms of what's involved in this context. So one of those very basic thing that one has to do in this context is maybe create like a device file that does basic things like void hard coding devices, getting the current device, getting the current device type, the basic things that you would need, defining backend dynamically, the RNG, the random number generation state handling, and then of course initializing of the send and receive channels. So things like that. That's pretty straightforward. So that's an example of the kind of thing that's very systematic, almost programmatic, and you can do it very easily. The tricky stuff happens more in, say, something like a file that's defining the parallel state, where you are trying to set up different types of tensor parallelism, pipeline parallelism, model parallelism, expert parallelism, all that stuff. And so here, because the collective communications have to be normalized, they work a little differently between XLA and CUDA. So you have to put in a little bit of effort where you can't just assume that you'll be using something like nickel. And so that requires a little bit more effort. But again, nothing that turns the code ugly or really just gross to deal with. But it's something that one has to kind of work through and make an effort. So I'll pause here and open it up for any questions or any comments, any feedback.
Perfect. Thank you so much. Let's see if there's any questions. Let's give it a minute or two. That was awesome, Ajay. Thank you so much.
Yep.
Maybe if you want to stop presenting too, that might be helpful.
Yes.
Did someone have a question?
Yeah, I have a quick question. Thanks, Ajay, for this amazing presentation. So one quick thing is that when you said that you make the scripts kind of accelerator agnostic and XLA enabled. So what accelerators do you cover? Like all possible accelerators, like most of the accelerators? How painful it is to enable XLA on it, or how easy it is to? Any learnings from there?
I'm not sure I entirely understand your question. Could you elaborate a little bit?
Yeah. So you said that you made the scripts accelerator agnostic. So do you and when you show the scripts, you say we can see that there are if statements saying that okay, if handle this different kinds of accelerators. So is that the scripts are being modified, or is that most of the scripts are being modified, like it handles most of the accelerators? So that's the.
Okay, got it. So at least in this context, the effort has been either to use CUDA as the mechanism to using accelerator directly, or using XLA. And in that context, at the script level, all you have to do is first automatically detect whether or not you are in the world of XLA. And if you're in the world of XLA, then at the script level, you may have to do at some places something like a mark step or things like that, and that's all you really need. Other than that, the thing that you have to do is to make sure that your devices are not hard-coded. They're not hard-coded to CUDA, and as long as your devices and random number generation state and things like are not hard-coded, there's nothing you actually have to do in terms of if, then, and so on, right? So that part is pretty straightforward. And surprisingly, even in the context of libraries, you don't have to do a lot of if, then, else. If you look at that example of Megatron LMX that I've shared, you'll see most of the if, then, it actually happens because of that library's desire to use multiple other dependent libraries like Transformer Engine, or not use Transformer Engine, or use Apex or not use Apex, not because of XLA and so on. So that was the very interesting revelation. And then the little bit of if else happens is because of the non-standard interfaces for collective communications between XLA and non-XLA. That's the only other thing.
Okay. Yeah, thanks for clarifying.
Yeah.
Any other questions?
Any feedback, any comments?
All right, we are out of time. So again, thank you so much to everyone for an incredible 2024. So let's make 2025 even more amazing. So please do reach out if you want to present at the next community meeting. Thanks, everybody.
Thank you, folks.